Welcome to Laser Safety Training, Laser Alignment. This training module provides guidance on how to align lasers prior to their use. The video will introduce you to some of the equipment used in laser alignment, as well as making you aware of some potential health and safety issues. Before commencing any laser alignment activity, it is essential that you make a plan and perform a risk assessment. This should be undertaken in conjunction with your laser safety officer. In this sequence, we are assuming you're starting from scratch, but often you will be realigning an existing system. In this situation, you would use pre-existing alignment procedures and plans. Your planning should take the form of sketching out the beam path in a lab book or directly on the optical table, with the beam switched off, of course. The act of drawing the beam path out like this should help you to identify the components needed to achieve your desired setup, and it should bring your attention to any health and safety issues to be included in your risk assessment. For example, it is advisable to ensure the laser source is pointing away from any doors and towards the room corners. This reduces the risk of a direct laser beam exiting the room. Once you have drawn out your entire laser setup, you're ready to begin your risk assessment. The aim of a risk assessment is to identify potential risks, how likely they are to occur, and then identify ways of eliminating or reducing the risks. This is a risk assessment. It shows an example of the process you should adopt to identify and minimize risk. Firstly, you need to identify the hazards and how people might be harmed. Next, you need to identify the people who may be harmed and under what circumstances. Then, the risks need to be evaluated in order to decide what controls and precautions are required. You will need to make a record of the findings of your risk assessment and implement them. Finally, you must review and update your risk assessment as necessary. Your risk assessment should detail any alignment best practice guidelines specific to your lab. This will include a risk hierarchy, detailing engineering, administrative, and personal protective controls. Prior to undertaking beam alignment, personnel must ensure that they have read and have understood the risk assessment. To minimize the risk in laser setups, make sure that any untrained people are not in the lab. Then it is advisable to remove any personal items that may reflect beams, such as a watch or jewelry. For visible beams, some people choose to use special laser alignment safety goggles. If you do, please be aware that you must still exercise caution, as they cannot protect your eyes should the laser power output increase for some unforeseen reason beyond the calculated limit for the alignment goggles. You can further minimize the risk of laser setups by ensuring large reflective surfaces, such as computer screens, are positioned above any beam paths to avoid reflections being transmitted around the lab. One of the best ways to de-risk your laser setup during alignment is to use Class 1 or 2 lasers. If this is not possible, another way is to significantly reduce the power output of the laser. Use a power meter to monitor the laser's power level and ensure that once it's turned down, it cannot be accidentally turned back up during alignment. If you cannot guarantee that this won't happen, make sure you put an attenuator in place immediately in front of the laser source, which reduces the power to an acceptable level for alignment. Please note that the external safety shutter and beam tubes have been removed for demonstration clarity throughout the video. Once you've finished planning and risk assessing your experiment, it's time to prepare the lab for the experiment, making sure to put in place any special precautions that were identified during the planning process. You can start by making sure the lab is tidy, giving particular attention to the floor area. You must ensure there are no trip hazards, as once the lab lights are dimmed for alignment of visible beams, they pose a much greater risk as you won't be able to see them so clearly. Also, keep in mind that wearing protective eyewear will reduce apparent light levels further and increase chances of a fall. Next, it is always advisable to put a notice on the outside of your lab's door to warn people that you are performing a laser alignment. A timestamp will reassure people it's not a permanent notice to keep them out. Once you've carried out any additional activities or precautions as identified by your own planning and risk assessment, you're ready to dim the lab lights and begin aligning your laser. Keep in mind that your eyesight will be affected by the low light levels in the lab, so move around the lab slowly and carefully until you're satisfied that you have become accustomed to the light. Before starting any laser alignment activity, it is important that the beam is orientated to run parallel with the table. Firstly, you need to decide the height at which you want your beam to travel around the table. You will need to take into consideration the minimum and maximum heights of the components you'll be using. Once you've decided on an appropriate beam height for your experiment, you can define this height with a pointing device. 2 mirrors can be used to make a beam run parallel to the table and slightly change the height of the beam from a bulky or non-adjustable laser source to match the previously selected beam height. Firstly, place a mirror at 45 degrees to the laser beam, close to the laser source. Make sure the mirror adjusters are about halfway through their travel. Use a diffusing card to check that the beam is hitting the center of the mirror. Next, set up your second mirror as far away from the first mirror as is reasonably practical. Use an optical pointer to ensure the center of the mirror and therefore the resulting beam will be at the required height. Then adjust your second mirror so that it is positioned at 45 degrees to the beam, making sure that the incident beam hits the center of the mirror. Using 2 mirrors together like this can correct any discrepancy of the laser's original height, angle or position, converting it to a beam parallel to the table traveling in the correct direction. It can be quite difficult to judge whether a beam is exactly parallel to the table using just your eyes, so you might want to use 2 irises to ensure the beam is parallel. The further apart the 2 irises are, the more likely you are to achieve an accurate parallel beam. The height of the irises are set using the optical pointing device set at the beam height previously selected. Position the first iris as near as possible to the second mirror, so you've got the beam passing through the smallest possible aperture at the center of the iris. Movement on the second mirror has minimal effect on the beam through the first iris. The first mirror is the centering mirror of the first iris. The second mirror is the pointing mirror through the second iris. Next, open up the aperture on the second iris so that the beam is passing through it. The beam position is then adjusted to pass through the smallest aperture in the center of the second iris. Once the beam is passing through the center of the second iris, you can be confident that the beam is parallel to the table, provided the 2 irises are sufficiently spaced apart. The further apart the irises are, and the smaller the aperture the laser is passing through, the more likely it is that you have a parallel beam. Components can be any standalone part of an optical table setup that can manage the path of the laser. Here we will discuss the use of mirrors, lenses, periscopes, and beam splitters in laser alignment. A key consideration for any alignment process is to ensure that all optical components are securely fixed to the table whilst the laser is in use. Mirrors. These are used to change the direction of the beam path. It is important that the laser beam is aligned with the center of the mirror. Before you turn the laser on, make sure that the screw adjusters on the mirrors are more or less halfway along their travel, so that you have the maximum amount of adjustment available once the laser is turned on. You must ensure that the laser does not wander off the center of the mirror, as this could cause potentially hazardous stray beams. Use cards to check for any stray beams. The next components to consider are lenses. These are used to focus the beam as it travels around the optical table. There are 2 types of lenses, convergent and divergent. First, make sure you turn off the beam, then remove the lens from its holder and then turn the beam back on and align it through the small hole at the center of the lens holder. Then turn off the beam, open the holder, and fit the lens. Once you turn the beam back on, make sure that it is passing through the center of the lens. Lenses often produce stray beams as a result of the laser reflecting off their back and/or front surfaces. You can set up beam dumps to catch these. The lens must be normal to the beam path. To ensure that this is the case, you can use double irises. Whilst the beam must be positioned at 90 degrees to the beam path, you must ever so slightly tilt the lens so that the beam is not reflected directly back to the laser source, as this can cause power instability and can damage some lasers. The next components to consider are periscopes, which are used to alter the beam's height. There is a special hazard to be aware of whenever you use periscopes. If they are used incorrectly, they can change the orientation of the beam so that it travels upwards at 90 degrees to the table, which can be hazardous if you get in its way. To avoid this happening, make sure you always have the top mirror in place and aligned in such a way that the beam travels parallel to the table, and make use of a vertical beam block over the top of the top mirror. The final components we'll be talking about are beam splitters, which, as their name suggests, are used to split off a proportion of the laser beam whilst not significantly deviating the direction of the main beam. Beam splitters are wedge-shaped, so that when the beam hits them, it reflects off the front surface first, then the back surface. The two reflected beams are physically separate. The reflection from the first surface is generally more useful, as it hasn't been distorted by travelling through the glass or silica beam splitter material. Once the beam is split, you can dump all extraneous beams into beam dumps and just use one low-powered beam for your alignment. It is important to note, from a health and safety perspective, that stray beams generated by reflecting high-power lasers off beam splitters can still pose an optical hazard. If you calculate that the reflected beams are a problem, you must use the same safety precautions as you would when working with a full power beam. It is much more challenging to safely align high-power lasers and lasers of certain wavelengths that are more hazardous than others. An ideal way to align these kinds of lasers is to put a housing around your setup to contain any stray beams, with motorized adjustment screws on any components that adjust the beam's path, and multiple cameras dotted around the table paired with beam splitters. It's best to place cameras before or after key components that change the beam's position. You can then safely monitor these cameras via a computer interface. This setup removes any risk to your eyes or skin. Beam splitter and camera combinations are placed before key components in the system to allow adjustment of optical components, remotely or otherwise, to bring beams into proper alignment. The other benefit to using cameras in laser alignment, besides the health and safety benefit, is that you can use them to very accurately determine the beam's position. Cameras suitable for the laser wavelength can be used as long as they have a high enough resolution to enable the beam to be viewed effectively. Most laser beams' diameters illuminate a large number of pixels, which can provide an accurate measurement of the beam's position. If the spatial beam intensity profile is very irregular, special software can be used to find the center of the beam as viewed on the camera to aid alignment. You can use this technique to help align both visible and invisible beams. And cameras in combination with remote control component adjusters can enable the whole system to be placed in a light-tight enclosure. This effectively removes the optical hazard of alignment. Next, we are dealing with aligning invisible beams. It is obviously much more of a challenge to align a beam that's invisible to the naked eye, but there are a number of ways to achieve this. Before we go into how to align invisible beams, it is important to take note of the unique health and safety issues that arise from their use. They can pose an optical and skin hazard if you get in their way, and because you can't see them, you can easily be exposed to them for longer periods of time than visible beams, and therefore they can potentially do greater damage. The neutral density filter attenuator shown ensures laser power is kept to eye-safe levels for alignment. The beam tube connecting the laser and attenuator has been removed for demonstration purposes. With this in mind, let's now look at what methods we can use to safely align invisible beams, using equipment such as fluorescent cards, cameras, collinear beams, and burn paper. You can use whichever piece of equipment works for you, and then perform alignment activities in much the same way you would if you were working with a visible beam. Firstly, you can use a viewer to reveal an invisible beam's path. There are various camera types available with differing wavelength ranges for viewing most wavelengths of laser. Viewers can sometimes be difficult to use with certain eyewear, so they may not be suitable for everyone. Another way of revealing the position of an invisible beam is to hold a fluorescent card in its path. The beam will appear as a bright spot on the card. You will need to move the card around once you have located the beam, otherwise the fluorescent effect fades. Care must be taken with cards, as some are reflective and can pose a problem with high-power beams. Choosing a matte-surfaced card is a good option. You can also use multiple cameras to align invisible beams, though this can be an expensive option. You can get various small camera units to place in your laser setup. You can monitor the position of the invisible beam by using cameras that operate on the same wavelength range as the laser you're working with. Burn paper, or thermally sensitive paper, is generally used with far infrared wavelength lasers, as these kinds of lasers are beyond the range of standard infrared viewers or fluorescent cards. Burn paper usually uses thermally sensitive printing paper, which goes dark when it is heated by the laser. Smoke isn't usually produced, but if the laser power is too high, then it can often trigger charring or ignition, which could set off smoke alarms. So use with caution. Thermally sensitive plastic sheets are also available. These employ liquid crystal technology, which temporarily change color in response to heating when placed in the laser's path. The properties of the sheet can be changed to alter the threshold temperature of color change to detect lower or higher laser powers. This module has provided you with a basic overview of laser alignment. We have emphasized the importance of planning and risk assessing prior to performing an alignment, of prepping the lab prior to starting your alignment, how to make sure your beam is parallel to the optical table using irises and the two-mirror technique, the various components you can use to align a beam, such as periscopes, lenses, beam splitters and mirrors. Never be afraid to ask colleagues for advice about individual components, as they often are a mine of information about safe handling and shortcuts to alignment. We've also covered the use of cameras in alignment to minimize the optical and skin hazard. And finally, we've given you some techniques to help you locate and align invisible beams. This concludes the module. For more information about laser safety, please contact your laser safety officer.